Hello everyone and welcome back to Total Organic Chemistry. In this video, I will be taking a look at the SN2 mechanism for nucleophilic substitution. By the end of this video, hopefully the questions that you will be able to answer are: first, how does nucleophilic substitution occur? What is the mechanism? And how can we use SN2 reactions to our advantage in organic synthesis? So if you need an introduction to nucleophilic substitution in the first place, please remember to subscribe to my channel and take a look at a previous video that I've uploaded on that topic. So let's get right into it. SN2 is an abbreviation for nucleophilic substitution, so that's SN, and the 2 stands for bimolecular. So it is one of 2 main mechanisms. We'll talk about the other one in a later video. But SN2 is the bimolecular mechanism for nucleophilic substitution. And so remember that bimolecular means that we have 2 molecules participating in the rate determining step. So that means we'll have a second order rate law for this mechanism. And another way you could look at that is that SN2 reactions are concerted, which means that they occur in one single step. And because they occur in one step, that means our nucleophile and our electrophile will both be included in the rate law. So let me show you an example of what I'm talking about. So say if we have a nucleophilic substitution with chloromethane, so I'll draw that here, just one chlorine atom on our methane base. And then say our nucleophile could be the hydroxide anion, so OH-. And like we talked about in the previous video, for nucleophilic substitution, that OH-, so the lone pairs on the oxygen, will attack the carbon on the electrophile and kick off the chlorine in the same step. So we can draw 2 of our curved arrows in the same step to show that this reaction is concerted. And the products we will get from this, remember, are methanol, so CH3OH now because we've substituted the chloride, and then we will get the Cl-, so a chloride anion, as a byproduct. And like I said, because the SN2 reaction is bimolecular, that means that the rate of the reaction will depend on the concentrations of both the nucleophile and the electrophile. So if we were to write a rate law for this reaction, we could write that the rate is equal to our rate constant K, which could be anything, times the concentration of CH3Cl, so that's our electrophile, times the concentration of OH-, our nucleophile. So if you doubled the concentrations of either of those, you would double the reaction rate. If you doubled the concentrations of both nucleophile and electrophile, the reaction rate would increase 4-fold. So a very important property of SN2 reactions is that the nucleophile attacks from the back of the leaving group. So if we drew a more detailed mechanism for our nucleophilic substitution that we just wrote down, we could draw our CH3Cl here, but this time draw in the stereochemistry. So we'll have those wedged and dashed bonds for the hydrogens, and let's say we'll have the chlorine pointing to the right. When the hydroxide anion attacks, it will attack from the left side, so on the other side of the chlorine. And before we draw the final product, let's draw the structure of the transition state of this reaction. So what we'll get is this carbon center, and the 3 hydrogens will be coplanar now. So they're kind of being pushed to the right a little bit, and in the transition state, they will all be in the same plane. And then the bonds to both the OH and the Cl will be partially formed or partially broken. So in this transition state, the carbon is forming a partial bond with the hydroxide, and the chlorine is partially leaving that carbon center. And maybe we could draw some partial charges here, so we know that the chlorine and the oxygen are both more electronegative than carbon, so we can draw in our delta minus for those, and then a delta plus for carbon. And when that chlorine finally gets around to leaving, then what we'll have is the hydroxide on the other side of the carbon. So that's what we call backside attack, or Walden inversion. So we've pushed those hydrogens to the other side, we've inverted the stereochemistry at this particular carbon. And this is what Walden inversion is an inversion of stereochemistry in SN2 reactions. And with chloromethane, this is not really a big deal because it's not a stereocenter in the first place, right? So it has 3 identical substituents, all those hydrogens, so it is not optically active. However, we could imagine any molecule that does have a stereocenter, so let's draw this molecule here, 2-bromobutane. And let's draw the bromine coming out of the page, and the hydrogen on that stereocenter going back into the page. So if we assign our priorities here, we know that bromine is going to be first, and we can label 2, 3, and 4. And if you need any help or additional review on labeling priorities for determining absolute configuration, please take a look at my previous video on that. So we know that now we've labeled the priorities and we can tell that this is an R stereocenter. If we take this compound through an SN2 reaction, we can use, for example, a nucleophile OCH3-, so that's a methoxide anion. And remember from the previous video, if you're doing chemistry in the laboratory, you can never have just a lone negative charge. There always has to be a positive charge to cancel that out. So in the laboratory, we would use something like sodium methoxide, NaOCH3. And because that's our nucleophile, it will again attack from the back side of the leaving group. So what we'll get is an inversion of stereochemistry. We'll get the methoxy group pointing now into the page, whereas the hydrogen on that stereocenter will be pointing out of the page towards us. And if we relabel our priorities again, and we can find, so oxygen is number 1, and 2, 3, and 4, we can determine that this is now an S stereocenter. And although the absolute configuration of this stereocenter has changed from R to S, it won't necessarily change from R to S or S to R in every case. So always remember to relabel your priorities before and after an SN2 reaction if you're trying to figure out the absolute stereochemistry of your reactants and products, because depending on what your nucleophile is and what your leaving group is, the absolute configuration could in fact stay the same. So let's take a look at another example using this 2-bromobutane, and we'll use the same enantiomer, so the bromine coming out of the page towards us. And let's say we want to synthesize this compound where the bromine is replaced by an SH group, so that's a thiol. However, you might notice that the SH group is on the same side as the bromine, and I just told you that SN2 reactions cause an inversion of stereochemistry. So how are we going to do this? Well, what we can actually do is do sort of a double SN2 reaction. So let me show you what I mean. We can treat this first compound, the 2-bromobutane, with something like sodium iodide. So to get that I- nucleophile, we know that halogens can act as nucleophiles as well. And that will cause an inversion of stereochemistry at that stereocenter. So we'll end up with the iodine on the other side, so pointing into the page, and the bromine will leave. Then what we can do is do another SN2 reaction. So we take that SH group, and again, the SH will attack from the opposite side of the iodine leaving group. So that means that the SH will end up on the same side as the bromine was originally. So that's one way that you can use two SN2 reactions consecutively to maintain the stereochemistry of your starting material. I'd like to talk about one more part of the stereochemistry of SN2 reactions, and to demonstrate that we can use this cyclohexane, the substituted cyclohexane. So let's say on the bottom carbon here we have a CH3 group pointing into the page away from us, and then on this carbon we'll have a bromine again pointing into the page. So this will be a cis substituted cyclohexane, because both of these substituents are pointing in the same direction, so cis. And if we treat this with sodium iodide again, So in our SN2 fashion, we will again replace that bromine leaving group with the iodine nucleophile, and it will cause an inversion of stereochemistry at that stereocenter. So our product will have the iodine coming out of the page towards us. However, if you noticed, we haven't performed any sort of SN2 reaction or any reaction on the other stereocenter. So the stereochemistry of this bottom carbon with the methyl group will stay exactly the same. It has not been affected by the SN2 reaction at the other stereocenter. So we end up with the trans isomer as a product. And that's something to remember, that SN2 reactions only affect the stereochemistry of the active stereocenter that you're reacting at. So hopefully you're now comfortable with the idea of SN2 reactions and the mechanism that goes along with that, as well as some of the stereochemical properties and kinetic properties of the SN2 reaction. So, as always, thank you again for watching Total Organic Chemistry. Please be sure to like and subscribe if you learned anything new. And also please consider donating to my Patreon page, which I will link in the description. That helps me continue to create these types of videos for you.